All right, so today we are going to talk about a rate proportional, and this is going to look very similar to what we did back in pre-calculus or in Algebra 2 or in chemistry class. It's these type of questions that you've done before. It's going to relate to what we did yesterday, but not as much as you would think. So it says the half-life of potassium is 1,350 years. If 20 grams are present now, how much would be present in 800 years? And so a reminder to do that, we use this formula right here. Y equals AEKT. You've seen some different letters maybe in that before, like maybe A equals PERT, PERT formula. You use that formula with money. You use that Y equals AEKT with more science-related stuff, and you can use some different letters. Doesn't really matter. The key to these types of problems is the first thing you need to find with them always is your constant, that rate of change. Okay, that's the K in this question. The K is going to tell you how fast does it grow or how fast does it shrink. And so for this question right here, we are going to find K given on that first statement. It says the half-life of potassium is 1,350 years. And so the A in this equation is what you started with. I started with 20 grams. The 1350 is the half-life, so that's what I plugged in for T. I'm solving for K. Then I got this 10 right here. How did I get 10? Half of 20. Half-life indicates that you have half as much as what you started with. And so after 1,350 years, I'd have half of 20. That's where I'm getting the 10 from. So once I've set this thing up, I now only have one missing thing. I only have that K. And so I want to figure out what K is. And so to find K, I'm going to get rid of stuff. I want to get rid of everything until I got K by itself. Daniel, what could I get rid of first here? Divide by 20. We want to get rid of that 20 on both sides. I'm going to divide by 20. 10 divided by 20 is, guess what? 1/2. That's why, again, half-life. 1350K. I'm trying to get K by itself. I need to get rid of something else. What else can I get rid of? E. Drew, how am I going to get rid of E? ln, the opposite of E is the natural log, so I'm going to take the natural log of both sides. Those things are going to cancel. I've got the I always do that. Natural log of 0.5 is equal to 1,350K. I want to get K by itself, so the last thing I'm going to do is divide by 1,350. And so in my calculator, I'm going to figure out what that value is. The key, the really important part of this question is not to round numbers in the middle of this problem. And so I'm going to type in the natural log of 0.5, close my parentheses, divide by 1350, and I get this decimal right here, negative 5.13442. All right? Don't let it scare you that it says e to the negative fourth. Remember that e to the negative fourth is just scientific notation. The negative 4 is telling you to move the decimal to the left 4 spots. It's this number right here. I don't care about that number either. I've got a calculator, so I'm going to let the calculator do all the work for me. And so my K is that negative 0.00005, whatever. I'm not going to write it down anyways because I don't really care. I'm going to use it right now. Once I've solved for K, I now want to know how much will be present in 800 years. So I'm trying to figure out how much do I end with. I'm solving for Y. So what I'm going to do is take that K that I just found right here, and I'm going to plug it in. And so in my calculator, I'm going to do 20 E to the K times T. So my K, I'm just going to hit the upward arrow and select that thing right there and hit enter. There's that K value. I didn't round it at all. It's exactly what it said. Times 800. I type it in, hit enter. 13.263 is my final answer. So how many grams are left? 13.263, or in other words, 13 grams. Questions on that problem right there? That is going to set us up for every question we do today. And so you need to be confident in what I just did there in order for us to figure out what's happening. Pull out your notes. All right. So here we go. Today, here is the connection between the bell work and what we did yesterday. Remember that we have a whole bunch of phrases for what we did yesterday. Yesterday, we solved the differential equation. We found the particular solution. We solved the initial value question. All of those things mean the same. We could also find the general solution. That means the same thing. Or we can do this. given the rate of change of y is proportional to y. That is a statement they will make. That concept means this. Rate of change of y, or in other words, the derivative, let's not cross it out, the derivative, dy over dt, is equal to, proportional to y. So k is some proportion, some number, times the y value. Dy over dt, the derivative is equal to k times y. Let's look what happens when we want to solve for y. In order to solve for y, I got to get rid of dy dt. So to get rid of dy dt, I need to integrate it. And in order to integrate it, I need to separate it. And so look what happened. We moved the y over. We moved the dt to this side. It gave me this thing right here. We separated. Then what do we do? Integrate. When we integrate both sides, dy over y gets you this. The integration of k. K is a constant. It's a number. And so it becomes kt plus c. We solved, or we separated, we integrated, and then this is not the particular solution. This is the general solution. So we didn't have to solve for c. We just got y by itself. So to get rid of natural log, we did e. To get rid of absolute values, we did plus or minus. They did some fun stuff with the exponent where we had the e plus c became times e to the c. And since it was times e to the c, we could pull that c out in front and give us that equation right there. What does this equation right here look like? What we just did. All right, we can use any fancy letter that you want to. You can use PERT, you can use that. It's all the same thing. When you start off with that equation right there, the dy dt equals k times y, that will get you this when you take the antiderivative of it. Okay? It is exponential growth formula. Everybody see what's happening there? Let's do it. So, oil is being pumped continuously from a certain oil well at a rate proportional to the amount of oil left in the well. And so normally they won't tell you the second part, but it's being pumped continuously at a rate proportional to the amount of oil left in the well. Or in other words, the rate dy dt is equal to the oil, which is the y, times a constant of k. K is that growth rate. How fast is it growing? How fast is it decreasing? Initially, there were 1 million gallons. 6 years later, there were 500,000 gallons remaining. It will no longer be profitable to pump oil when there are less than 50,000 gallons. Everybody understand what's happening? I'm going to do this first part without you writing it down in an attempt for you to stay awake. Everybody good with that? So just follow along. We are given this thing right here, dy over dt. We are trying to write an equation in terms of y. What do I need to do with that equation to write it as y? Not the derivative. I need to integrate it because it's dy dt. So I'm going to do this super fast. Okay? Super fast. Dy over dt is equal to k times y. Oh, I want to integrate that, so I'm going to separate it. And then I'm going to integrate it. The integration of dy over y is the natural log. Absolute value of y is equal to the integration of kdt is kt plus c. Everybody agree with what I've done so far? If I want to get y by itself, I'm not solving for c here because I want to write this in terms of y. I don't want to figure out what c is. It's a general solution. I'm going to get rid of the natural log, so I'm going to do e to both sides. I'm going to get rid of the absolute value, so I'm going to go plus or minus. I've got e to the c, so I can pull that constant out in front, and I get that thing right there. Notice that what I did was get us back to this same formula that we started with in Belwick. When you see this problem, you don't have to integrate it. Okay? If you know that the rate is proportional, you know that the antiderivative of this is that y equals AEKT formula. If you want to use different letters, use different letters, but it all means the same thing. We're all getting back to that point right there. Everybody see where I'm at? Once I've gotten that, now we're going to write an equation in terms of y with the amount of oil remaining in the well at any time t. So t is my only variable that I'm allowed to have, is what they're saying. I want to know how many barrels I have left, or how many gallons I have left at any time t. So I want to figure out an equation with just t. So I need to know a starting amount. How much did I start with? $1 million. I only want T to be a variable. That means I need to know what K is. Did they tell me my constant growth rate? No. I need to find that. That is exactly what we did in bell work. We are going to find our K. And so it's E to the K. Well, if I want to solve for K, that means I need to know my T and a Y. I need to know some time and how much did I have at that time. 6 years, 60 or 500,000 gallons. So I'm going to plug in 6 and 500,000. Solve for K. Do that now on your calculators, please. To solve, I'm dividing by 1 million, which guess what gets me 0.5. To get rid of E, I'm taking the natural log of that 0.5. And then to solve it, I'm going to divide by 6. And so in my calculator, I am taking the natural log of 0.5, and I'm going to divide it by 6. When I do that, I get this decimal. It's negative because I'm decreasing. The amount of barrels or gallons is going down. I do not want to round that number at all. All right, so right now, I'm going to make sure that I keep it as many decimals as I can. So K is equal to negative 0.11552 ... It's not ending. Okay, if this were a free response question, I could round it, but it's in the middle of my question right now, so I'm going to leave it. My job is to write an equation for Y in terms of the oil remaining at any time T. So my answer to this question then is Y is equal to my starting amount, 1 million, E, that K value, negative 0.116. I'm going to round it right now. I know it's not really rounded, T. That's my equation that I'm dealing with. That right there will tell me, any time that I plug into that will tell me how many barrels I have left. That's what that equation is giving me right now. Part B says, at what rate is the amount of oil in the well decreasing when there are 600,000 of gallons of oil remaining? I am talking about a rate. I want to know at what rate. Which equation up here is going to tell me a rate? The derivative equation tells me rates. The dy over dt equation is what I really want to use here. It says dy over dt is equal to K times Y. I want to know the rate. I want to know this thing. So if I want to know that thing, I better know my K and I better know what my Y value is. Do I know what my K value is? Yeah, I just found it. It was that negative 0.11 number. Okay, do I know what my Y value is? Yeah, what's my Y going to be? 600,000, because I want to know what the rate is when there's 600,000 barrels or 600,000 gallons. That's what my Y is. So the K is that negative 0.11552 number times 600,000. If I put those in and I hit enter, it's going to give me my answer. So I'm going to go 600,000 times, I'm going to just move my cursor up and I'm going to select that K value because that's what I want to use and hit enter. 600,000 times that gets me that right there. Does it make sense that that answer is negative? It's telling me the decreasing rate. That's what the rate is of the barrels. It's or the gallons. Oh, I keep saying barrels. It's annoying as can be. It's decreasing. It's a negative number. Negative 69,314.718. $69,314.718. We need a label. dy, change in Y. What is changing? What's the Y value represent? That's the gallons. And dt stands for the change in time. What's my time in this thing? Years. It is gallons per year. That is how many gallons we're decreasing every year at that moment in time when there were 60,000 barrels, 600,000 barrels. In order to not lose money, at what time T should no oil be pumped from the well? I want to talk about time. Which one of these equations is going to help me with time? The first one, that Y equals equation. allows me to plug in any time that I want. And so I'm going to use that equation. I want to know when it's no longer profitable to pump gallons. I want to figure out the T. So I'm going to use that equation. I'm going to find out the T. What is the Y going to be then? The point at which it's no longer profitable, which is 50,000 gallons. 50,000 gallons remaining, that's when it's no longer profitable. So all I'm doing now is I'm solving this equation. 50,000 is equal to 1 million. How many zeros? That's too many zeros. Now we're good. All right. E to the K T. I know what my K is. Do your math. Solve for T. Go. We set up that equation right there. I divided by 1 million. That got rid of the 1 million. To get rid of the E, I took the natural log of both sides. So now I have natural log of 0.05. To get rid of K, I'm dividing by it. So in my calculator, I'm taking the natural log of 0.05, and I'm dividing it by that K number again, which is this number up here, that negative 0.011 number. I don't want to round it. Oh, no. Oh, well. Yeah, we screwed that up. Natural log of 0.05 divided by that number. There we go. Hit enter. 25.932 is going to be how many years I can pump before it becomes not profitable anymore. Questions on that first? It is really more pre-calculus than calculus. Once we get past that initial step, you can separate and integrate every time. It's going to get you the same formula. All right, let's flip it over. Example 5 is a little bit more fun than I want to do right now. If you're looking for a challenge, number 5 is great. Let's look at example 6. The volume of a cube is increasing at a rate proportional to its volume at any time t. It's increasing at this rate. The volume is increasing. So in other words, that means dV over dt, the change in volume over time, is equal to what? K, the proportional to the volume. And so it's proportional to V. It is KV. That is my initial equation. You can use Y's if you want to use Y. V stands for volume. All right, that's our initial stuff. In the end, we are answering a question about what is the volume. What is the volume? Right now, this equation tells me a rate. I want to know the actual volume. So what am I going to have to do with this rate to talk about the volume? Integrate it. Guess what the integration of KV is going to get you? Y equals AEKT. Could you use some different variables in there to represent volume? Sure. I just know exactly what those letters mean. This A stands for the starting amount. The Y stands for the ending amount. That's it. You can use whatever letters you want, but it's the same formula we've always done. Again, technically what we did is we took the antiderivative, but we just sped up the process. I knew what was going to happen. I want to know the volume. 8 cubic feet originally. And so for A right here, I'm going to plug in 8. Did they tell me anything about my constant rate? What my K is? So that means the first thing you probably got to do is find K. In order to find K, I need 2 things. I need to know an ending amount and a time. Did they give me another ending amount and time somewhere in that equation? 12 cubic feet after 5 seconds. So I can plug in 12 for the feet and 5 for the time. Solve for K. Once you've found K, figure out how much is left with 12 seconds remaining. See what you can do. We solved this thing, and so to get K by itself, I took 12 and divided by 8. To get rid of the E, I took the natural log. To get rid of the 5, I divided by 5. When I typed that into my calculator, I got this value right here, 0.081 whatever. Does it make sense that that number is positive?
Yes.
What's happening to the volume of our cube, or of our shape here? It's getting bigger. It's increasing. That's why it's a positive number. Once I've found that, then all I'm doing is taking that K and plugging it in right here. And so my formula is going to look like this. 8E to the k, so I'm just going to go up there, times my time, 12 seconds. I hit enter, 21.169. And that's cubic feet. So feet cubed. That is my final answer here. Which makes sense. It's bigger than what I started with, and it was directly proportional to it. Questions here? The key to that, if you can recognize it and just skip ahead, it's going to save you a lot of heartache. Let's do one last problem here. All right, and this one's a lot different, so we're going to switch gears. If you've gotten frustrated for a second, these will be a little bit different. I like this question. Example 9 looks much different than the other ones. If you need some more practice, 7 and 8 are going to be similar. We'll go back to those in a second. But number 9 is the one we're looking at right now. Consider the differential equation. dy over dx is equal to that thing, for which the solution is g of x. I hate when they do that, but they call it a solution. What is g of x compared to that dy dx, do you think? It's the y, it's the integral, it's the antiderivative. Or in other words, if you take the antiderivative of that, it gets you to g of x. They call it the solution. It's the y value. It's a weird thing that they do. Which of the following is true about the particular solution that contains the ordered point 0, -1? So look at your multiple choice answers. They're asking basically two questions. Is it increasing or decreasing? Is it concave up or concave down? About g of x. If I want to talk about g of x, what do I need to describe about g of x to decide if whether it's increasing or decreasing?
Is it positive or negative?
What is positive or negative? G prime. What's g prime the same as? dy over dx. The slope. dy over dx is the derivative of g of x. That's going to tell me the slope. And so I'm going to plug into this formula, dy over dx. What am I going to plug in for x? 0. And for my y, I'm going to plug in -1. I'll let you keep going with that one. You can handle that. Then the next question that we have to answer is concavity. It's either concave up or concave down. What do we need to look at to talk about concavity? The second derivative, the derivative of the derivative of this dy dx equation. So I need to take the derivative of that. What is the derivative of dy dx going to get me? Yeah, g double, that's fine. We can call it g double prime. G double prime is equal to, what's the derivative of x going to get me? 1. The derivative of x is 1. Plus the derivative of 2y. That's implicit. It is 2 dy dx. Finish that problem. See what you can do with it. To determine whether it's increasing or decreasing, we need to look at the first derivative. When I did the first derivative, what was my value getting me? -2. If the first derivative is negative, is it increasing or decreasing? Decreasing. So it's not A, it's not B. Those are both increasing. So to talk about the next one, I want to know concave up, concave down, or linear. And so basically, is the second derivative positive, negative, or 0? How could I figure out what the second derivative is going to be? Evan? You can plug in -2 here. You could plug that whole equation back in, but we already just did that. We know that it's going to get us -2. So this is 1 minus 4. That gets me -3. So is it concave up, concave down, or neither? Down like a frown. The second derivative is negative. Therefore, it's concave down. Negative makes you